Hi, my name is Nikhil. I'm a PhD student in UC San Diego, and today I'm presenting our work, JIGGLE, an active sensing framework for boundary parameter estimation in deformable surgical environments. So let's consider the problem presented by these two deformable tissues. Just by looking at them, can you tell me where they're attached to the environment? Well, no, not really, right? Because at first glance, they're pretty much identical. To do this, you actually need to actively interact with the environments. Now, the next natural question that arises is how do you really decide what action to take next? These are the questions that surgeons think about all the time. Just look at the video here. They need to constantly manipulate the tissues to understand the structure and attachments in the environments. And these attachments are actually really important to surgery, as a large part of operations are spent either removing these attachments to get to the site of the surgery or resect some sort of diseased tissue, or create these attachments using techniques like suturing. Inspired by this, we present JIGGLE. Our method uses the discrepancy between simulated and observed interactions to compute a probabilistic update on boundary attachments, which we then leverage to compute safe future actions. Our method is divided into two components, estimation and active sensing. Let's start by talking about estimation. We represent our deformable tissue using a fully differentiable PBD or position-based dynamics simulator. We model our boundary attachments as springs of varying strengths that attach to the tissue with virtual particles that are fixed to the environment. We probabilistically track the boundary attachment parameters using an extended Kalman filter. This contains two steps. First, a prediction step that evolves the parameters using an assumed motion model, and second, an update step that incorporates new observations. The key component of computing these updates involves computing a Jacobian, J, which we here are easily able to obtain by leveraging the differentiability of our PBD simulation. We demonstrate our estimation method on real-world experiments. We sutured chicken skin pieces onto chicken thighs to create ground truth attachment points. Notice that the uncertainty decreases in the deformed regions, which are shown in blue, while the estimated attachment points, shown in purple, begin to closely match the true sutured region. Now that we figured out estimation, let's move on to active sensing. Our active sensing algorithm aims at maximizing information gain while respecting safety-critical constraints in surgery. For information gain, we prioritize deforming uncertain areas of the tissue. We enforce safety by constraining the spring energy on the estimated boundary constraints, and add a soft constraint to penalize actions that actually exit the safe workspace. Our final objective is written as a sum of all these terms. To select the next action, we start with an initial set of large action samples. Each action is then iteratively refined based on its gradient with respect to our objective function. We then select the best sample and take a step in its direction. Here we show some results in simulation on active sensing. The video shows regions of increased confidence in blue, and the graphs show entropy reduction and boundary energy over time. Notice how our method takes actions to intelligently decrease the entropy while keeping the boundary energy below a certain level. The estimated shape uncovered by our active sensing strategy matches the partial ground truth. Our approach also supports topological changes in the boundary conditions such as cutting. We incorporate priors on the topological change into the Kalman filter's motion model, as shown here. In this example, we're using our method to iteratively estimate and then cut attached regions of the tissue. As a summary, we present JIGGLE. Our approach leveraged the differentiability of PBD simulators with an extended Kalman filter to estimate boundary parameters, which we used to generate an optimization-based entropy minimization strategy.